Assalamu alaikum. Hello, everyone. We continue with the topic of classification methods. So we have been talking about decision trees and how they are used as classifiers. There is one problem with decision trees, which is the problem of overfitting. So when you get so much concerned about what your training data is telling you, and your training data may not be a good representative of the whole population. So you maybe build a very complicated tree that tries to fit every training data, and then it doesn't generalize well outside the distribution of your training data. Okay, so to overcome this problem, then there are some algorithms that work with one tree and try to avoid the problem of overfitting by using different things such as pruning and tree pruning and early spacing. But there is a method called random forest. This method actually aims at minimizing the overfitting by actually not relying on a one tree. So the idea is to build multiple trees, okay, and then do a majority vote at the outcome of these trees. So the idea of random forest, and that's where the random forest is coming from. It's like you have multiple trees, you're building multiple trees, and then everyone is telling something about the label of an input sample, and then you do majority vote and decide based on that. The random forest is actually a method under the umbrella of in-sample methods. Okay, so in simple methods, actually in simple methods do not rely in one model in order to make a decision. So they rely on the idea of building different models and then do some aggregation to the output of those models in order to make a final decision. Okay, the aggregation could be majority voting for a classification problem, for example, or averaging for a problem like regression problem. Okay, so how do we build multiple trees from our training data samples? The idea is simply you sample randomly, like you take n samples randomly from your data set, and you do random sampling with replacement. So the same data sample can be chosen in multiple trees, but with different combination in terms of the other samples that is chosen with. Okay, so we randomly sample like a number of samples for each tree, and also we randomly choose like number of features. Okay, we don't include all the features. We choose m small such that m small is much less than m capital, where m small is the number of features we have chosen for a certain tree, and m capital is the total number of features. So we are randomly sampling samples. We're randomly sampling as well as features, and we build different trees. Okay, and then we train all of these trees. Then for a given sample, we feed it to all of these trees, and then we actually, if we are running decision trees as classifiers, then we do majority vote to the outcome of these trees in order to make a decision about the class of an input sample. By the way, there are also there's what we call like decision regression trees. Okay, but we are not considering regression trees for this course. But if we are running the regression trees, then the way we aggregate the outputs of all features is not of all trees is not to do majority vote, but to do average to the to average the outcome of all of these trees. But again, here in this course, we are only focusing in decision trees as classifiers. So we run multiple trees, and then we get the outcome of every tree, and then we do majority vote. What do I mean by majority vote? Let's assume you have 10 trees, and you have two classes, okay? And you feed one sample to each tree, and then let's say seven trees are telling you that this sample belongs to class 0, and 3 trees telling you that this sample belongs to class 1. Then you will go with the decision of the 7 trees. Okay, so you do you rely on the decision of the majority of the trees. Okay, that is the idea of random forest. Okay, let's look at how we actually build a random a classifier using a random forest from scikit-learn library. Okay, so from scikit-learn dot in simple, we import random forest classifier. So it's under in simple methods. Okay, and then simply the only difference is in this code here. Okay, so we load our data, we encode our categorical attributes into numerical ones using one hot encoding, and here we actually build the object for the classifier. So we define the number of trees. Okay, here number of estimators is equal to 6. So we are building 6 trees. Okay, so every sample, we will feed it to 6 trees, and then we get the outcome of each one, and then we do majority voting to come up with the final decision. The criteria we use is entropy, and everything else is the same. Okay, so here we build the object of the classifier, and here we fit the classifier in our training data, and then here we are plotting the trees. Okay, since it's more than one tree, we are creating a number of subplots. We did that many times in the past, and then we iterate over those subplots, and for in every subplot we plot the tree, one of these trees, one of these estimators. Okay, so we set the maximum depth to be 4. Okay, so we don't go beyond 4, we stop there. So we're kind of like also doing like early stopping here for every tree. Okay, and that's it. We run this code. I'm running some other simulations, so the computer is a little bit heavy today, but that's it. That's the idea. So we're gonna get 6 trees, okay, plotted here. Let's just wait a little bit and see. Yes, these are the estimators, and we have explained decision trees in the past. Okay, so that's the idea of random forest. Now we come to another method that is used for classification called naive Bayes, okay, or like Bayesian learning, okay. So the idea simply relies on Bayes' theorem. This is Bayes' theorem. So the probability of a class C given a predictor X is equal to the conditional probability of predictor X given class C times the prior probability of class C or the prior probability of class X, okay. So here, P of C given X, this is the posterior probability of class C given the predictor X. P of C is the prior probability of the class C. P of X given C is the likelihood, which is the probability of the predictor X given the class C, and P of X is the prior probability of the predictor X. So the word naive is coming from the assumption we make that all of these different features are totally independent. Okay, they are not dependent on each other, and so they contribute equally and independently to the decision. And that may not like always hold in practice in the practical examples. So if that holds, we will get good results. If that doesn't hold, the results may not be so great. We always can test the generalizability of the model on our training data samples. One thing to mention here, independency is stronger than correlation. So you may have two random variables, X and Y. They independent, then they are uncorrelated, okay? If they are independent, then they are uncorrelated, but sometimes they could be like there could be dependency. Okay, so in other words, like independency leads means already uncorrelation, but sometimes you have two random variables. They could be like there could be dependency, but it's not captured in the correlation because, as I said, correlation may fail to capture the nonlinear dependency. Okay. So anyways, so if we have features that are totally independent of each other, okay, then this may give really good results, but that may not always hold in the real life, okay? So if I have multiple features, so let's look at when we have more than one feature, then the probability, the posterior probability of class C, given all the predictors, will be equal to the likelihood, the probability of all predictors given the class C times the prior of C over the joint probability of all predictors. Okay, this is a joint probability. Okay, the probability given the joint probability of all the predictors. Okay, and this is the joint probability of all the predictors given class C, and this is the joint probability of all the predictors. Under the independency assumption, then the joint probability will be the multiplication of the individual probabilities. That's why this reduces to this under that assumption, which may, as I said, which may not always hold. Okay, then it will this joint probability will be the multiple of the individual probabilities. So in the denominator, we'll have probability of x1 times probability of x2 and so on. And here probability of x1 given C times probability of x2 given C and so on. Okay, now let's look at how we construct a naive Bayes classifier. Okay, so we first convert the data into frequency table in order to compute the probabilities. And again, when we are computing the probability from the data samples, what we are computing is actually an estimate of the actual probability, because we don't really know the actual distribution. We are just like provided some data samples, and from there we are estimating the probability. But yeah, so that's an estimate of the actual probability. It could be accurate estimate as well as it may not be inaccurate, but that's what we are working with. So we compute the frequency, we create what we call the likelihood table. We will see it down, and then simply we will compute the posterior of every class with respect to the given values for the input features, and the one that has the highest posterior probability is the one we would choose as the outcome or the class of the provided sample. Okay, let's look at how we compute the all like probabilities. Okay, so we're gonna work with this example here. We load this data. Okay, so we have those 4 features and the target variable. Okay, so now focus in one attribute. Let's focus in the temperature here. Okay, so simply if we want to look at the probabilities here, we can simply call the function value count. The return of this function is a data series where the labels are the different categories here, and the values are the occurrences of each one of them. Okay, mild has occurred 6 times, hot 4 times, and cool 4 times. Okay, same for the target variable. We run value counts, so we have yes and no. Yes has occurred 9 times, and no has occurred 5 times. Let's look at the cross table between these two. So here we display the cross table. We call the function cross tab, and then we pass temperature as the rows and play as the columns. And here, this is what we get here. Simply, this represents what? So like the number of times in which temperature is cool and play is equal to no is only 1. That happened only once in our data. The number of times temperature is cool and play is yes is equal to 3. So there were 3 samples in which like when the temperature was cool, play was yes, and so on. From that, we can compute the likelihood table, the probabilities, right? So here we just showing like all the choices for the temperature. So we have hot, mild, cool. It's the same thing. We just flip the order here, okay? Or like the order is not exactly this, but it's the same. Like these are the choices for the temperature, and these are the choices for the target variable play. It's either no or yes. Okay. So when the temperature was hot in our samples here, when the temperature, we find like the number of samples in which the temperature was hot. There are 4 samples, 1, 2, 3, 4. Okay. For 2 of them, the value for play was no. For the other 2, the value was yes. So 2 samples with temperature hot and play no, and 2 samples with temperature hot and play yes. Okay, we do the same thing for mild and cool, and these are the numbers we got. Okay, now if I want to compute the probability of the probability of yes given hot, that's equal to the probability of hot given yes times the probability of yes over probability of hot, right? Let's compute each one of them. Let's start with what's the probability of yes. Okay. So now we have yes and no, right? So in 9 samples, we sum those. This column. This is the column of yes. Okay. 9 samples out of the total 14, the value for play was yes. And for 5 samples, the value was no. So then the probability of yes is equal to 9 over 14. And the probability of no is equal to 5 over 14. Okay, so now we have the probability of yes and probability of no. Now let's compute the probability of hot given yes. Given play is equal to yes. So we want the probability of the temperature is equal to hot. We want this one. Okay, is it this one here? The probability of temperature equal to hot given play is equal to yes. Let's look at this here. Probability of temperature equal to hot given play is equal to yes. Okay, so play is equal to yes 9 times. Two of them, in two of them, the temperature was hot. Therefore, the probability of hot given play is equal to yes is equal to 2 over 9. Okay, 2 over 9. Okay, so now we are ready to compute. Yeah, one thing is left. Okay, what's the probability of hot? So what's the probability of hot? So probability of hot, okay, like what are the different choices? Okay, so we have 4 samples where the temperature was hot. Okay, 6 samples temperature was mild, and 4 samples temperature was cold. So the total number of samples is equal to what? 4 plus 6, that's 10, plus 4, that's 14. So then the probability of hot is equal to 4 over 14. So as you can see here, the numbers here, this is the probability of hot, this is the probability of mild, and this is the probability of cold. This is the probability of yes, this is the probability of no. So the probability of hot is equal to 4 over 14. Okay, now we are ready to compute the probability of yes given hot. Okay, that's equal to the probability of hot given yes, which is 2 over 9, as we computed here. Okay, times the probability of yes, which is 9 over 14, 9 over 14, over the probability of hot, which is equal to 4 over 14. So now we came up with the probability of yes, play is equal to yes, given temperature is equal to hot. That's equal to 0.5. Okay. Now, okay, so now if I'm given a sample, okay, and I rely only on the temperature, and I computed the probability of yes given hot, okay, then I compute the probability of no given hot, and in fact, I here, since I have 2 classes, no or yes, then I can just take 1 minus this, which is equal to 0.5. So when the temperature is hot, okay, the class, which class we choose, they are equally probable. The probability of yes and the probability of no, when the temperature is hot, they are both equal to 0.5. Then we simply assign this sample randomly to one of these 2 classes. But for example, if the temperature is mild, the probability of yes is equal to 2/3. Okay, and the probability of no will be 1/3. So then if the temperature is mild, then we will choose the class to be yes. Okay, temperature is cool, the probability of yes is equal to 0.75, 3/4. Okay, so the probability here is high. So then we will assign this sample to the class yes. Okay, now that by the way, I actually could have from this table computed like the probability of yes given hot. Okay, so here we have used the theorem, but this is a very simple problem. We can actually compute from the table the probability of yes given hot. So here is hot. Okay, these 2 samples. So 4 samples. 2 of them, the value for play was yes, and for 2 others the value was no. So then the probability of yes given hot is equal to 2 over 4, which is equal to 0.5. That's another way, like you get it directly from the table. Okay, so how do we do that with the code? So we load our data. Okay, and then here we split the data before we do transformation. It's fine, we could have done the transformation first, and then we came up with our input, the matrix of input features and the target variable. But here, like we did it in, like we split them before we do the transformation, and here we did the numerical transformation. And since really here we're using a probability, and we're going to use what we call categorical naive Bayes classifier, which considers like all the values that we give are categories. It doesn't matter here, like we can use ordinal encoding. We know ordinal encoding will introduce an order. For example, if I have one feature that has 3 choices, and we have actually here, then they will be encoded in 0, 1, and 2 based on the alphabetical order, because here we're not really building a specific order. So we're just calling ordinal encoder. By default, it will like order them based on alphabetical order. But since these numbers will not be involved in any multiplication or any mathematical operations, it's just computing the probability, these numbers are like, this variable is of type nominal, okay? So these numbers are there just for identification. So it's okay here in this case to use ordinal encoder as well as label encoder. Okay, so we do label encoder for the target variable, so it will be encoded into 0 and 1, and we do ordinal encoding for the features. So we will see, like for some features, we'll see like one of them or two, I don't remember, they have 3 categories. So we will see 0, 1, and 2, but those numbers, we're not introducing an order here, because simply we are using categorical naive Bayes classifier, which actually deal with those different numbers as different categories. Okay, the order will not cause an issue here. Hopefully that's clear. So yeah, as I said, we import the categorical naive Bayes classifier. Here we create the object, okay, and here we fit it in our data. Okay, so simply here, these are the input arguments we pass for the naive Bayes classifier, the categorical naive Bayes classifier. Alpha, this is actually just like, as far as I remember, this is like the smallest probability. Maybe you can, because sometimes if the probability is 0, you have division here. You divide with 0, that will create an issue. So alpha here is introduced to avoid that issue, okay? So you put minimum there, so you avoid dividing by 0. Class prior is equal to none. So here we're not assuming any assumption about the prior, okay? The probability distribution of any of the input features. Simply, we want you to learn it from the data. Fit prior equal to true. So there is no an assumption. If this is true, then the assumption will be they are uniformly distributed, okay? For each feature, like the distribution is uniform, but we're not assuming that. We are actually learning the distribution from the data samples we have. So we will use the samples we have to compute the probabilities, okay? So that's it. We create the object, we fit that in our data, and then here, that's it. We came up with the 2 classes, okay? And that's it. Here, actually, we build the classifier, okay? Here, what comes after is just like some printouts. So here, like we call the function inverse transform in order to like relate the transformed classes, the 0, 1 to the original ones, which were yes and no, as we'll see in the printout later on. So here we are printing them out. This is printing a new line. We print the statement, and here we're printing the classes, okay? So whatever inside curly brackets here is taken as a Python expression because of the if we pass here, okay? So if you want to print out the probabilities, then we need to access this property here in this object, the classifier, the class log prior, because it returns the classifier saves the log prior, the log probability, not the probability. Therefore, if you want to find the probability, we just need to take the exponential of that, right? So if I have log x, then I want x, then I take e to the power log x, e will cancel with the log, and I will get x. So here we are printing the probabilities, okay, of the 2 classes. And here, simply, like we iterate over all the features by calling, by retrieving this property here, this object, feature log probability, and we are defining rows and columns for the tables, as we will see down. So we're plotting these tables, okay? Okay, so the probabilities, the likelihood probabilities for each one of the features. So simply we iterate over them. The rows are defined by the classes, yes and no. and the columns are defined by the different choices or unique values for each feature, because we're iterating over all of the features. Every time we're calling different feature, we're accessing that feature, we're retrieving all of the possible choices, and then we sort them. These are the columns. And then we are building a data frame for each one. Simply the values are the probabilities rounded, okay? And that's it. So that's for every like for every, so all this, the columns are defined by the unique values for each feature, and the rows are defined, or the indices are defined by the classes. Okay, and the values are the probabilities. That's it. So this is it here. These are all the likelihood probabilities. Okay, that is for the naive Bayes classifier. Somehow I feel like I forgot something to mention here. But yeah, let me print out this to see, to look at the, after the encoding. Let me do display X after encoding here. Let me run it again. Just to look at the data after, yeah, here. So the first one has 3 categories. The first one was what? I forgot. The first one was outlook. Yes, it has 3 choices: sunny, overcast, and rainy. That's why we see like here 0, 1, and 2. Okay, and same for the second one. I think the second one was what? The second one was the temperature: hot, mild, and cool. Okay, that's it. Somehow I feel I forgot to mention something, but yeah, if I remember next time in the next lecture, I will go back to that. But that's the idea of the naive Bayes classifier. So in maybe okay, let me stop here for today. Next time we will talk about different metrics we use uh, to evaluate our classifiers, and then we will go over these case studies. Let's stop here. Thanks for watching, and see you next time. Salam alaikum.